All right. Hi, everyone. So I'm Lauren, and we also have our tutor Daniel here as well. And he's going to be managing the chat for the time being. So if you have any questions, feel free to ask in the chat. We'd be more than happy to answer any questions that you got. And today we're going to just kind of do an overview of some things that you should know for the first exam and kind of going through some of the sample questions that we were provided as well, right? These guys over here. And if you have any questions of your own, feel free to let us know at any point. Otherwise, we're just gonna kind of get started with this stuff and go from there. So first things first, a lot of this exam is going to be going over the different states of processing, right? So when an instruction comes in, you want to make sure that you're familiar with the different steps that it goes through, right? You probably are familiar with fetch, decode, exec, mem, and write back, right? These are extremely important to know because you're going to do a lot of going through these steps, whether it's in a single cycle processor, where it's just one instruction at a time, or a pipelining processor, which is when we're able to overlap these guys a little bit more. So going through a little bit of what's happening at each of these states, right? So we know that we have different types of instructions. We have loads, right? And we have stores. So with a load, right, we're taking information from our main memory to our CPU. We're literally loading it in. For stores, it goes the other way around. We're writing data from the CPU into our main memory. We also have other instructions too that can often change what instruction comes next. Because usually it's just one after another, after another, after another. But when we have branches and when we have jumps, this works a little bit differently. When we have jumps, let's go through the simpler option. This allows us to jump from one instruction to another. You're probably very familiar with the label X by now, right? If let's say this line of code is labeled with like an X, like that, this is just saying if I say jump to X, it's saying skip over these two lines and go straight to this line labeled with the X. So jumps are always going to jump to that position. Branches are a little bit different. These are when we actually have conditions. So if, let's say, our register R1 is greater than 0, actually, we can write that out as branch greater than R1, comma, 0, right? And this is just literally the same thing as this. It's saying we only will do the branch if this Boolean value is true. So think of it just a normal if statement, right? If this, then that. That's quite literally exactly what's kind of going on over here as well. So again, we did load, we did stores, branches, jumps, and finally, the last type is called an R type. You can think R like arithmetic. And this is just your usual math computations that you'll be doing. So if I said register 1 plus register 2, that says that I do R1 plus R2. Whatever is in this register added to whatever is in that register. And now this could be stored in register 1, let's say. So this is an R type. And these are the main types of instructions that you want to keep in mind. You're going to be asked to go through a bunch of these guys during problems. So it's very important that you kind of know them and also know which instructions have which states in them. Because while yes, there are 5 states, not all of these guys go through them all the time, as we're going to see in this question over here, actually. So let's just quickly go through that, and then we'll go on to the first problem, which actually goes right into that. So load instructions go through the entire sequence. So a load is going to do fetch, decode, exec, mem, write back. I'm going to go through the entire instruction because I have to fetch the instruction from the memory. I have to decode what are its operands and operators. So operands are what are the registers we're doing things on. Operator, what are we doing to the registers? We have exec, right? Once we decode, now we can actually place the corresponding bits on the wires that need to be done. For instance, if I know that I'm going to be loading, right, I can now say that, okay, this is going to be a read operation. I'm not writing anything, I'm reading. So let's say for the control wire, I can put down that it's a read operation. Next, I have mem, right? Because I actually now need to go get the memory address that this is coming from main memory. And then finally, write back. I have to actually get this state, get this and write it to my CPU, right? So with that, right, we know we're going to be going through all 5 stages for that. Stores is going to be a little bit different, right? We're going to do ourselves fetch, decode, exec, mem. The reason for this is because we're still going to do our fetch or decode or exec, same thing, but this time we're not writing back to the CPU. We're going to memory and we're leaving the data there. So the data goes to memory and that's it. It stays in memory. So what happens in memory stays in memory. So because of that, we are not going to be writing back when it comes to that. Next, when we have branches and jumps, right? Jumps are super easy because I'm only going through 2 states. I'm going to be doing a fetch and a decode for a jump. And the reason for this is I fetch the instruction, I decode and I see it's a jump, and then I do the jump. So that's literally it. There's nothing to exec here because I'm not doing any arithmetic. Branches are going to be a little bit different because branches are going to actually have that extra arithmetic step, since we have to actually evaluate what this Boolean is saying. So they're going to actually have the exec step. So I fetch the instruction, I decode what's going on. I know it's a branch, so that means I have to do this Boolean in the exec state. And likewise, right, can't forget about our arithmetic, R types. I'm going to fetch, decode, exec, but I'm going to do one extra step here, right? After I do the arithmetic, I actually have to store this somewhere. And where am I going to store this? Well, over here, this instruction has 2 sources and a destination. I'm not just going to do the operation and then just leave it at that. I actually have to store it somewhere or it's not going to be any good for me. Think about doing a problem and you don't store your operation in a variable, you're just going to lose it. So because of that, we have to also do a write back. Notice, we don't do a mem state. This is because there's no reason for us to go into a mem state. These were already loaded at some point, as we're going to see with this problem right here. Because of that, we don't need to worry about actually going into memory aside from the original fetch that's going to be to get the instruction. So we fetch the actual instruction, decode, okay, we realize it's R type, exec, do the arithmetic, I skip mem, and I go right to write back. I write the result to the destination register. Okay, so this is the foundation for doing all of these types of questions. So before we go on, any questions about this? I'm going to also put this in the chat as well, since it's a good resource to have. You probably have it in your notes, of course, but just so that you kind of have it when I clear the screen out. So now we go into the actual question itself, right? We have over here for a 32-bit system, the operating system loads the following program at offset 2696, executing on a single cycle processor. Assume that each data memory location contains an initial value of 6, and each register, if not explicitly initialized, has an initial value of 2. Okay, got a lot of information here. So how do we interpret this? Well, first things first, we know it's on a 32-bit system. And if you remember from class, right, every single time that we go from one instruction to another, we have to change our program counter, our PC. And usually the default is always PC plus 4. You've probably heard the professor say PC plus 4 about 100 times. And the reason for this is because this is saying go 4 bytes ahead, not bits. So remember, there's 8 bits in every byte. So if I have 4 bytes times 8 bits, I get 32. Well, look at that, a 32-bit system. So that means by doing the number of bits divided by 8, I can get how much the program counter must increase each time. So that means after every one of these instructions, I'm going to be plussing 4 bytes. So that's something good to keep in mind, right? In case it asks for a question like, hey, what is the program counter at the end of this instruction, let's say, right? Well, I know it's 2696 here, right, at the start, and I could just keep plussing 4, 4, 4, 4, and whatever that is what the program counter is equal to, which is probably going to be a question later on. So that's something good to keep in mind. We also know that this is a single cycle processor. And what that means is that I'm going to be doing each instruction in its own time. I'm not overlapping states. I'm not sure if you've learned pipelining yet, but if not, right, you know, the difference between single cycle is the next instruction after doing fetch decode exec mem write back. The next instruction is fetched in the cycle after we finish writing back. Nothing is done simultaneously. And this is to ensure that, you know, we don't have any overlaps, because that could be a problem, because you can't have like 2 fetches going on at the same time, right? If they were all just like fetch decode exec mem write back, wouldn't be an issue. But we're going to learn later on that it's not that simple in life. So what we do know is single cycle processor, right? After I do this instruction, my next instruction does not start till over here. So that's good to keep in mind. And then finally, probably the most important part, each data memory location contains an initial value of 6, and each register, if not explicitly initialized, has an initial value of 2. So what this is saying is that each data memory location is 6. What's a data memory location? Well, when I am taking in a value, right, it's going to be at 6 if I'm going to be talking about the memory address itself. On the other hand, every register, right, we know registers in this case are represented by a T. And when I did it, I just said R, T, R, same thing. S is often used as well. If you see a $sign before it, that's just a register for that. So each of these registers are going to be having an initial value of 2. So this is good to keep in mind, because we want to essentially keep track of what each of these values is having, because we got to see how long, like what is going on in each step. So let's first take a look at what these questions are asking. Oh, Abid, you raised your hand? Okay. Yeah, again, stop me at any time if you have questions, not a problem. Okay, so, okay, let's start out with the first two questions over here, right? First, calculate the total memory reference count for the above execution. All right,
Hello?
so
Oh, okay.
yeah,
My mic is working now. Sorry about that. But I was asking, do you recommend for the exam to like annotate the question itself, like how you underlined or circled certain information?
yeah, absolutely. I think it kind of helps to write things out, especially because there's a lot of information in the question.
Okay, thank you.
Of course, as you do the questions, you'll find like kind of a method that works for you best. So kind of go from there. All right, so first we're calculating the total memory reference count for the above execution. Okay, so when we talk about memory reference count, this is how many times we're going into memory. And this happens twice, depending on what instruction we're talking about. We know that both mem and fetch are two states that have to go into memory, meaning that if you're doing a load, you could end up going twice into memory, right? Fetch to get the actual instruction, mem to get the actual data reference. But when it comes to others, you might only be fetching, right? Every single type of instruction is going to fetch and decode for that matter. But not everything will exec, mem, or write back. So we want to keep in mind what types of instructions are these and calculate it based on that. So first things first, we know we have over here, LI means load immediate. So this is a load, but there's a difference between load immediate versus load word. So that's LI versus LW. Load immediate is loading a constant, just a normal number. Load word is loading from a memory address, meaning that only load word is going to end up going into mem. Load immediate is just taking this normal number. 300 is just a number. It's not anything special. It doesn't come from a mem address. So that means for each of these load immediates, while yes, it is a load, we're only going to be going into our main memory for just the fetch state. So not for the mem state. So this guy over here, we know is going to be one fetch, right? And I'll do that in green so that stands out. The next one, same exact thing. We have another load immediate. This guy's only going to be a fetch. Now the third instruction is going to be a little bit different. This time I have a load word. So this time, notice how this is a little bit different, right? This is saying load our word into register T2. And for this, right, we know that we're going to be going into a fetch and a memory. And the reason for this is because it's a load word. I have to actually go into memory for this. And this is denoted by the fact that I have parentheses around here, right? So because of this, right, this is going to actually be loading in a memory address. And inside a memory address is some value, basically. So with that being said, right, we have a fetch and a mem in there. So we also have for the next instruction, an add instruction, right? And that's an arithmetic. So remember we have fetch, decode, exec, and write back. So no mem state, so this is just going to be fetch. Next one is a load word. This we know is going to be a fetch and a mem. Mul means multiply, right? This is another arithmetic type. Just like last time, we know that this is going to be just fetch. Okay, next we have add immediate. Same thing. This is literally going to just have to be the same exact thing for an R type, so just fetch. And finally, BGT means branch on greater than. This is a branch. Branch we know does fetch to code exec. So that means we're only doing fetch to go into memory. Okay, count. How many times have we gone into memory? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Now, sometimes you might be asked for the data memory reference count versus instruction. And the only difference between this is I combined, because it was total, the fetches and mems. Data talks about the times you go into mem. Instruction reference count talks about the times you fetch. Because remember, what are you doing? You're doing fetch the instruction. When you're doing mem, you're actually going to be getting the memory address. So the data that comes from there. So if, he asks something a little bit different, then data versus instruction. Yes, there's a question. Oh, I think your microphone is a little off.
I could barely. I don't think I can make any. I don't think I can hear anything legible from that.
Yeah, me neither. If you want to put your question in the chat.
Yeah, what was that?
Not too sure.
Oh,
Okay, anyway, right now from here, right, we're going to do the number of cycles. So I'm just going to clear my screen. Right. So we know total number of cycles, right, is based on the number of instructions that we have, right? This is single cycle processor, meaning that it's one cycle per one instruction. So now we just have to count how many instructions there are. So I'm going to write out pretty much how many instructions that we got for this, right? We know that we have 1, 2, 3, 4, 5, 6, 7, 8, right? But we know we have a branch here. And this could mean that if this is true, we could end up having a loop. So that means we actually have to evaluate this. Because if that branch ended up being true, then that means it definitely would not be 8. It would be a lot more because of how many times the loop would go. And this is why we have to keep in mind the values that they tell us, right? Because we know that each memory location has an initial value of 6, and each register has an initial value of 2. Okay. So we first start out with load immediate, T0, and we're loading 300 in there. So I'm going to just write on the side, T0 is equal to 300. Okay, next one, T1 now is going to be loaded with 0. Okay, cool. Next, we load word T2 to T1, right? So, hang on 1 second. All right, so this is a little bit different than the notation that I'm familiar with, but what this is referring to, I believe, is this is saying that I am, this is like the offset of that register, right? So this is saying that I am 2 bytes, aka 16 bits, away from the value I'm loading here, right? So I'm loading into T2 the value denoted by the mem address of T1, offset by 2. So that kind of seems like a lot, but the reason we're going to do this is we're breaking it down. We have parentheses here. Anytime I see parentheses around something, I know this is immediately going to be a mem address. So parentheses means a mem address. So yes, there's a register in there, but T1 we know holds 0. So I could replace what's in these parentheses instead of T1 just with a 0, right? And then I also note that I have a 2 here. So this is my offset. So I'm saying go to mem address 0, offset by 2 bytes. Why 2 bytes? Well, okay. We know that in this case, right, we're going to be having our mem address offset by this guy over here, what's on the outside. And this is done also down here too, which we'll get to. This is not offset by anything because it's by 0. Now, mem address 0 was not given to us directly, but it does say over here, assume that
Excuse
each
me?
data memory location contains an initial value of 6.
What do you mean by offset? Like, do we add 2, or is the 2 just the address?
So it specifies how many bytes away are from, like, it is the mem address is from. So instead of being in mem address 0, right, this is 0 bytes, I'm going to be in plus 2 bytes away. So exactly, we're just going to add this together, and this is going to just become mem address 2.
Okay, gotcha.
So I'm
Thank
just going
you.
to write that as M2, right? That way we know it's mem address, not a register. And it just says, assume that each data memory location contains an initial value of 6. So nothing was changed here. I'm just using 6. Totally fine. Okay, cool. So now we go to the next instruction. Add destination register T1. We're going to add together T1 and T2. Okay. Oh, sorry, I forgot to load the value of this into T2, right? So all this is saying is we found that this was from mem address 2, right? And mem address 2 has a value of 6. This value gets loaded into this destination register. So T2 has a value of 6. Now when we do the next part, right, T1 plus T2, and that gets added into T1. Okay, so T1 is 6. Oh, sorry, 0. 0. And then we know that T2 is 6. So now our new value for T1 is 6. So I changed the 0 to a 6 now. Okay, so we're done with that instruction. Now we're moving on to here. We
Quick
got
question.
ourselves, yes.
What happened to the plus 2? Like, I thought T2 was 2 because we did a offset of it.
So
Or am I just bugging?
no, you're right, but we offsetted the mem address. So remember,
Oh, it's in the memory. Okay, got it. Okay, I got confused. I thought T2.
yeah, this is probably the most confusing thing, right? We had 2 parentheses T1. We have to interpret this as a mem address. This is saying the mem address represented by what's in T1. Well, what's in T1 at that point was 0. we offset the 0 by 2. So all this entire thing is saying is mem address 2. Mem address 2, we know, has a default value of 6. So what are we loading into the register? We don't load the address, we load the value of what's in the address. So that's why we load the 6 that came from mem address 2 into T2.
Okay, got it. Yeah, the notation just confused me. Thank you.
Yeah, no problem. This is honestly very confusing, and honestly, if you want to just kind of take a step back and go through it a couple of times, it kind of makes it a little bit easier. But the key to remember is parentheses mean mem address. So it's the mem address denoted by whatever's in T1, and then
Okay.
offset by those two. Okay, so we were on load word. T3 is going to be our destination. And now we have this the same notation, 0 parentheses T0. But notice, again, parentheses. This is once again going to be an address. So first things first, what is T0? 300. Right? So this is going to be mem address 300. The 0 shows that we're not offsetting this by anything. So it's just going to be mem address 300. Mem address 300, again, initialized at 0. We haven't changed it at all, so no need to deal with that. Okay?
Wait, I thought the mem address would be 0. Why is it 300?
So we add what's on the outside here, not multiply.
Oh, okay.
Yeah, I know it looks like it's multiplication, but this is just the offset, and when we offset something, it's based on adding. Yeah, so again, this is it is confusing notation. So let's just break it down one more time, right? How did I get this? First things first, this is a mem address. I see parentheses. Let me interpret what's in register T0. We know it's a 300 from up here. Mem address 300, offset by 0. Okay, so that means it's not offset by anything, so it's just 300. So that's how I got 300 as that. And we know that's just 6 because, again, it's an initial value of 6. Now this value, which again is 6, the value inside the mem address is getting loaded into T3. Okay. Now we go to the next step, right? This is again another arithmetic instruction. We have multiply T1 and T3 and store it in T1. All right, what is T1? Well, T1 we changed to be 6, right? T3 is also 6. That means 36 goes into T1. So I'm changing 6 to be 36 now. Okay, second to last instruction, add immediate. This is saying add, or technically subtract, a -2 from T0 and store in T0. Okay, cool. So this is just literally saying T0, which is 300, -2. That becomes 298. Cool. Next instruction, branch on greater than. Now this is going to tell us, are we going to be ending here at 8 instructions, or are we going to be doing a loop? And you can bet that you're probably going to be doing a loop, but again, we have to find out. This is saying branch on greater than, right? If T0 is greater than 0, right? This has the $sign, but this is just the value 0, right? So if T0 is greater than 0, boom, we have to go and branch. Okay, well, at this point, it's 298. That is definitely greater than 0. So I have to branch all the way back to E1 and do all this over again. And you're probably saying like, oh my gosh, wait, how many times I'm gonna have to do this like 100 times? Like, what the heck? No, 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 you don't have to do it 100 times. You just have to recognize the pattern of what's going on. All of this stuff doesn't really matter at this point. The part that matters is these two instructions over here, because the only thing I care about is the value of t0 being greater than 0. And t0 is only getting changed in this second to last instruction. So everything else, well, yes, I'm going to be doing 1, 2, 3, 4, 5, 6 instructions over and over again. I only care about doing those last two and finding out how many times this is going to be happening. So if I know that every time this loops, it's going to be -2, -2, -2. Well, 300 divided by 2 is 150, meaning that this is going to be looping 150 times until we finally get to 0. Once t0 is 0, it's no longer greater than 0. So at that point, I'm not going to branch and I'm ending because this is the last instruction. Thank you, Daniel, for answering the questions in the chat.
If you don't mind, can you just explain which notation told you that it's looping? So I just can make a note of it.
Absolutely. Branch greater than. Anytime that you see a branch, this is your key. Find out if it is indeed looping or not. Remember, the loop only happens if this is true. Think of it as an if statement. If true, do the loop, do the branch. Otherwise, you don't do the branch. And we know that this value is going to always be greater than 0 for 150 times, because each time we're subtracting 2 from 300. So it's going to do this it's going to do 300 minus 2, 298 minus 2, minus 2, minus 2. It's going to do this 150 times. So I'm going to be looping this 150 times until this is false, and then I stop the loop.
I got it. Thank you so much.
No problem. So if this was the flip side, if this was branch on less than or branch on equal or something like that, right? Then we would never have branched in the first place, because of course 298 would not be equal to or less than 0. So that's why you have to trace the code first before you go any further. And I'll let you in on a little trick with a lot of Vivek's exams. It's going to be very similar to this format in the sense that you have a bunch of instructions that you really don't care about, and there's only one instruction that is actually changing the value of t0, because we only care about t0. I couldn't care less about t1 or t3. The only reason I traced through these guys is because it's good practice, and there are questions that require you to do that, right? If this was like a later question, I probably would have just kind of skipped that, honestly. But in reality, looking at this question, you have limited time. So I would just be like, okay, skim through. Oh, I see a branch. So I know that if this branch is true, I might be looping a bunch of times. Otherwise, I'm only doing it the number of instructions. So with that being said, I have to find out, am I looping this or not? And I look immediately and I say, well, I initialize t0, which is dealt with down here with 300. This doesn't require it. This doesn't require it. This doesn't. Boom, t0 is changing. These two instructions are the only ones I care about. That's the way I would approach these kinds of questions. Well, I can't guarantee it's going to be like that. There's probably a pretty high chance that you only need to care about a small subset of the actual instructions.
One more question. I was always told, like, for a lot of Vivek's tests to like double check because it's easy to make mistakes. Is that true as well?
I'm sorry, repeat yourself.
I heard from like other friends that took Vivek that it's easy to make like mistakes on an exam. So I heard it's like to always double check yourself. Is that true?
Yeah, I mean, for all questions, yes. With these, it is very easy to mess something up. For instance, if I forgot to do an instruction, or maybe I initialized the wrong value and you're looping on those wrong values, it could cause some problems, but you can still get partial credit. So, use your time effectively. Don't get bogged down on one question, but if you have time, definitely check your work. Yeah, so a question that was asked, greater than, equal, or greater than. So we have branch on greater than, branch on less than, and we have branch on equal. And there's also branch on not equal. These are the only ones that you'll really be using, I think. We don't have like a greater than or equal. And if it was, it would be specified here. These are the only four that you really will need to know. Greater than, less than, equal, not equal. And you're just doing a simple Boolean statement. So. Yeah, and exactly. $0 is just zero, right? It's just the register that is actually reserved for the value zero, because think about it, zero is used very frequently. So you need kind of a value for that. I mean, you could have also used like a register for it, like how we had T1, but it's good to know both ways. Okay.
I just want to make sure before we move on. The answer to the second question is 150, right?
Let's find. Oh, well, actually, no. So the 150 is showing how many times we're looping. So
Oh, so
that's
it's not the
saying
cycle.
exactly. The cycle is how many instructions are getting executed. So I know that this part, this red part over here, is getting looped 150 times, right? Everyone gets how we got 150 times, right? We went from 300. How many times can I subtract 2 out? 150 times, right? I just did 300 divided by 2. So I have 1, 2, 3, 4, 5, 6. 6 instructions, right? 6 instructions are going to loop 150 times. Now, I can't leave out these 2 instructions up here, these 2 load immediates. Note that they're outside the loop. Why are they outside the loop? The loop starts and ends with E1, right? E1 is a label. So that means this whole thing is the loop. That is the 6 times 150 part. What are the leftovers? Those 2 load immediates. Plus 2. That's your final answer. So total number of cycles for a single cycle processor. Remember, 1 cycle per 1 instruction. I'm going to just find the number of instructions that are executed. And usually this is going to be just counting the number of instructions executed, but you have to be careful with loops because as we saw here, that loop was 150 times. If I just said 8, right? 6 plus the 8, plus the 2 is 8 total instructions, that would be extremely off. So you have to make sure that you don't kind of do that. Alrighty. So with that being said, what is the final answer for the first question? Total memory reference count. We had a fetch. There was a fetch here. Okay, well, there was a fetch for everything. 1, 2, 3, 4, 5, 6, 7. Actually, wait. So actually, remember before we found the memory reference count for doing this, but we have to keep in mind that they said for the above execution. Well, technically, this was executed 6 times 150 plus 2 times, right? Those are the number of instructions. So I have to actually, when I say the total memory reference count, I have to adjust that based on the amount of instructions. So let's go through it really quickly, keeping that in mind, right? And the reason I say this is because when we did this, right, I know that each of these instructions is going to have a fetch, right? So all of these guys needs to have a fetch, but only some instructions, the load words here, are going to have mem. And the reason for this, right, is what we had before. Remember, only load words or store words are going to really be going into memory. Branches, jumps, and R types are not. So the only times that I have load words are for this instruction and this instruction. Everything else is just going to fetch. And when we talk about memory reference count, we want to talk about the amount of times that we're either in fetch or memory, right? This is our instruction memory reference count. This is our data memory reference count. And if we add these together, we get our total memory reference count. Okay, well, start out with the first two, load immediates. Remember, load immediate, I'm not going into memory, I'm taking these values here. Okay, so I'm only fetching for these two. So that means there's going to be a fetch here and a fetch there. So 2. Now I deal with my loop, right? So I know that this is going to be looped 150 times. But how many references are in this 150 times? Well, load word is going to have 2. I'm going to have a fetch and a memory. Load word, a fetch and a memory. Everything else, this add is only going to be a fetch. This add I is only going to be a fetch. This multiply only a fetch, and this branch only a fetch, because these instructions don't go into memory. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. So every time that I do this red section, this loop, I'm going to have 8 memory reference counts. And then I multiply this out. You don't have to do this on the actual exam, the actual arithmetic, the actual multiplication. This is honestly fine to leave as your answer. The professor said that you're more likely to mess up the calculation and get it wrong. So just do yourself a favor and just leave it like this. So with that being said, well, yes, if I did this whole thing only once, the answer would have been 10, because technically I have to do this loop 150 times. The 8 memory reference counts within this loop are going to be also looped 150 times. So that is the final answer for the first question. So we have the 2 plus 150 times 8, and the second question is 6 times 150 plus 2.
So wait, for the first question, is it 10 or 2 plus 158 times 8?
This part.
Okay.
If I was only doing it once, then it would have been 10. But because I have to take into account that I looped this 150 times, it's going to be this. And again, leave your answer like this. Do not solve it. I had an exam the other day, and I literally said that 9 times 4 was 45. Yeah. I promise you I can do actual calculus and actual math, but my brain was not working. I hate to say it, you are usually at your dumbest point during exams because you're very stressed out and it's very easy to overlook that stuff. So don't worry about the simple arithmetic. Just focus on doing the question itself. Okay. With that being said, right, let's move on to the next part. So for the entire execution, provide the memory reference string. Okay, so definitely got to clear this out a little bit. Too much annotation. So for the the memory reference string, all this is saying is the amount of times that I am going into this is saying the addresses that I am going into memory for. So when we had over here, right, we went into memory to get memory address 2, right? And then we also went into memory to get 300, right? So when we say the memory reference string, I'm literally just saying, give me all of the addresses that I go into in my memory. So with this being said, right, I know that when I do this loop, right, I start out with E1, and this is load word to offset register T1, right? So this is always going to give me 2 offset 2 plus whatever this value here is. So with that being said, right, I know that I'm going to be changing this kind of every time because I'm adding a value here, and I'm also adding a value. I'm also multiplying a value here. Just double check something really quick because it seems like it's changing way too much, honestly. Okay. So we know that there are 2 memory addresses we have to keep in mind. This T1 and this T0. Let's start out with T0 because it's a little bit easier, right? What's going on with T0 is every single time we are doing T0 minus 2. So the first time we did this, right, it was 300, mem address 300, and there was no offset on this 0. Okay, cool. So every time I loop this, I know it's going to be 300, 298, 296, etc. We know that every time that I get a memory address, it's based on whatever T0 is. So whatever T0 is going to also be what my memory reference string is. So I know the first part of this, at least, is going to just literally be the values of T0. So I know that for part of this, I'm going to have 300, 298, 296, etc. Right? And the reason I leave spaces here is because I also need to keep in mind that in between these guys is going to be the values of T1s. Because I want to say all the times that I go into memory. Right? These guys all came from T0. But now what we got to do is we have to say the part that is dealt with T1 now. Now, T1 is a little bit more confusing, but let's trace what's kind of going on here. We know that the first time we go through it, T1 is 0, right? That was the first value of T1. We know then that we changed that to 6 because we had added T1 and T2 together. And T2 had a value of 6, right? So it became 6. Then we know that we also had multiplied it by T3. What was T3? Also 6. So every single time that we are accessing this, right, we're doing these two operations to it. And that means that we're multiplying, we're adding 6 and then multiplying by 6 every single time. So the next time I get to this part over here, we know that my mem address is going to be 36, right? And let's just do one more iteration of that just to kind of bring the point home, right? I know that over here, right, is going to be 36. I'm going to add T2, right? So this is going to be another 6. So 36 plus 6 is 42. And then I'm going to also be multiplying T3, which is 6. So 42 times 6. And that's 12, 24, 25, 252. Okay, and that's honestly all that we need to really show at this point, just kind of showing a pattern that every single time, right? What memory addresses are we accessing? T0 is super easy. All I'm doing is subtracting 2 every single time, and that changes the mem address that's accessed over here. T1's a little bit more difficult because I have 2 places in which it changes every time, and those have to be taken into account, and we have to do that manually. Obviously, because this is looping 150 times, you are not supposed to write out every single change, but you just want to show a pattern. And I'm doing that right here. I'm showing that I have the T1, then the T0, then the T1, then the T0, and I'm showing the values at each of these places here. And then again, dot, 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 dot. As long as you just show a few values of that, that's honestly totally fine. Because again, you can't, you're not going to be able to write this out like 300 times. Okay, good.
Yes.
Yeah.
Fantastic. All right, so let's take a look at the next question here. Provide value of all CPU registers and memory bus for each of the execution stages for instruction 3. Okay. So instruction 3 is this guy over here, right? The E1. Let me just clear out a little bit of this clutter. Okay, so of all CPU registers and memory bus for the execution stages for instruction 3. Okay, so what we want to say for this one over here.
Excuse me, Lauren, but can you just clear the whole screen? It's starting to get really hard to follow along.
Gotcha. Okay, yeah, don't worry, we're good. Yeah. Okay, so this involves us tracing the registers for this guy over here. And we're going to be going through all of our states. So remember, what are our states? We have fetch, decode, exec, mem, and write back because this is a load word instruction. So we want to take into account what's kind of going on as we're doing this, right? So CPU registers are just my T1 and my T2. My memory bus is telling me the address in which I am going to. So when I fetch this instruction for the first time, right, the memory bus is going to have the program counter's value. because the program counter is telling me where am I going? And we know what the program counter is because we know it's this number over here, 2696 at the start. So if I were to go until the third instruction, right? We know here it starts 2696, right? Then from there, we're essentially just going to be plussing 4 each time, right? Because we went through with the program counter, it's always +4 on a 32-bit operator. So if I plus 4 on that, this gets me 2700. And then plus another 4 gets me 2704. So at the start of this guy, the program counter is going to be 2704. And this is what's going to also be the memory bus. The memory bus is going to take the value of the program counter to go into memory and fetch the instruction. Now, at the end of this, at the end of the fetch instruction is when this gets iterated to the next value. So the key thing here is that provide value of all CPU registers and memory bus for each of the execution stages for instruction 3. It doesn't say beginning or end, which is honestly a key that we're kind of missing out on, because if it's the beginning, it's going to be 2704. But if this is the end, remember at the end of the fetch state, this gets another +4 added to it. I would honestly write out both if he doesn't specify, but just keep in mind at the beginning, it's 2704. At the end, it's going to be 2708. Okay, our CPU registers, right? T1 and T0 are going to still have our original values, right? T0 is going to be 300 and T1 is going to have 0 because these were initialized over here. And T2 is not initialized to anything. So what is the value that they told us to assume is register has an initial value of 2. So because T2 was not initialized yet, we haven't done this instruction yet. We're in the middle of doing it. This T2 is just going to have a 2. Okay, that's going to be fetch. Now then for decode, right? What's going to be changing here? Well, now we're going to realize what the operands and operators are going to be. So at this point, we know that our memory bus program counter, it's going to definitely be 2708 at this point, because at the end of the fetch state, this gets changed to 2708. So I'm going to be leaving that as 2708, right? And these registers are still going to be staying the same, right? The only thing that's going to be a little bit different here, right, is our operators and our operands are going to be defined. So I'm going to be finding my source and my destination. My source is going to be this over here. My destination is going to be this over here. Right? That's what I realize at that point. And these guys, the T0, T1, T2 are going to be all the same still. Okay, so we have fetch and decode. Next, we're going to be doing exec, right? So at this point, right, we're going to be actually putting the values onto the wires because we know we have to travel into memory. So my memory bus now is going to be having the value of my source. What's the value of my source? Well, now I actually have to do the math. Over here, I just left it as the whole thing. Now I realize this is going to be 2 offset of 2 of register T1. Okay, well, what was register T1? 0, right? So this is just going to be 2 plus 0, right? Wait, did I do that? Yeah, okay. So this is going to be our address, mem address 2. And this goes on the memory bus. This is the destination we're heading to in the next state, which is going to be the mem state, right? And at this point, right, everything else is still the same. All the T's are still the same. And now we're good to go into the mem state, right? At this point now, we're going to be going to mem address 2 and bringing it back to the CPU. So our mem bus is still going to be address 2. And at this point, right, we know that we're going to be heading back to our destination. So again, this is why it matters if he tells you beginning or end of the state. At the beginning of the mem state, we're on our way to this address. At the end of the mem state, I'm at the address and I have to go back now to the CPU. So again, if this was beginning, it would be 2. But if this is end, this would get replaced by my destination, which is going to just be T2. So membus is either equal to 2 or T2, which is our destination. And again, this depends on whether he asks if it's the beginning of the instruction or the end of the instruction, because it makes a difference, because there's a lot of moving parts that are going on, and these values are changing mid-cycle, mid through these different states that you're going through. So once we're done with the mem state, right, then we have our last part, which is going to be our write back, okay? And this one now is going to just be, now at this point, we know our membus for a fact is going to be T2, right? At this point, we're well on our way back to the CPU. So I know for a fact that this is definitely going to be where my membus is. Also, again, doesn't matter beginning or end, because if I'm at the beginning, my destination, T2, is still going to be the same. It's going to be equal to 2. But if it's at the end, this would then get replaced by the up-to-date value, which we know we got from the memory address, right? All the memory addresses had a value of 6. If this was at the end, T2 would be 6. So again, this is why it's very important to know whether it's the beginning or the end. And of course, T0 and T1 are always still going to be the same because they're not changing in this instruction. So that's what we want to essentially be doing. If he asks a question along those lines, we just want to kind of track what's going on with these registers. This is a little bit more involved than what we did a little earlier, right? Because we're actually going through all of the parts of the instruction, but that's also why he only asks you to do this for one instruction. Otherwise, it would take forever. Okay. All right. I'm going to skip these last 2 questions because I'd like to kind of move on to another topic as well, since I want to make sure we have enough time, right? When they say the Z ALU registers at the end of the exec stage for instruction 6, right? Just a quick little thing. We know an ALU instruction, if I have something like this, right? This is going to be my destination, but before it's put here, right, it gets put in a temporary Z register. You know how on R-type follows fetch, decode, exec, and then write back, no mem? During the exec state, before we write back, we put it into a Z state. All that's just saying is do R1 plus R2. Get that result, and that's equal to your Z. So the Z is just a temporary register. That's all this is asking for. So you trace the code up to instruction 6, like what we done, and then add together the 2 source registers, and whatever that value is going to be your Z. And then the program counter, again, we went through this. Every time that I go through an instruction, I start out at 2696. And every single time that I do an instruction, I iterate by 4. The key here is the last iteration of the loop, right? So with this kind of question, we want to remember that, right? If this is 2696, right? This is 2700, 2704, et cetera, et cetera, et cetera, et cetera. Every time I loop back to 2704. So this essentially gets looped 150 times. But at the end here, when I finally stop, I realize, okay, this is the last time I'm doing the loop. I'm ending at this point. I will go to the next line of code. Well, what's the next line of code? It's whatever this is plus 4. So if this was 08, 12, 16, 20, 24, I plus another 4, because remember, every single fetch, we're going to be plussing 4. So this is going to leave me with 27, 28 as my next line of code. Yes, there's nothing there. And that's the point. That there's nothing there, so that tells you to stop. So that's what's important to keep in mind about the program counter. I wanted to just go through that quick.
So wait, what would the answer be for that particular question? 270.
27, 28. It's
27,
one.
28?
Yeah, it's plus 4 after this bottom instruction right here.
Okay.
Because remember, at the end of every instruction, at the end of every fetch, we're plussing 4. So if we realize, okay, we're done with this one, we're going to the next one, I'm not looping anymore, then I just plus 4. And that's the end of the code. So he might ask like, oh, give me the program counter at some random spot around here. Just realize that's what you want to do for that. And remember, it is based on the bit system. It is not always going to be 32. If it is 64, I need to do 64 divided by 8. That becomes 8 bytes, meaning I plus 8, not plus 4 at the end. So be very mindful of how many bits the system is, because he will absolutely try to trick you up on that. So it is almost 2:30. I thought we were going to get through a little bit more, but since there is a lot here, this is the bulk of it, honestly, knowing these states. So it is good that we went over this, but I want to hear what you guys want to go through, since I think we'll probably have time for one more of these large questions. So you tell me what you want to kind of go over.
I want to do more on the cache mapping, because we just learned about it. So it would be nice if we just went over a review about it.
I agree. I want more time to spend on cache.
Yeah, it's just so recent, and we barely had practice to do it as well.
Sure, definitely, we could go over these. All right, so for cache mapping, we're given the following memory reference string with cache size 4. Calculate the total memory access time, given that the time of a cache is 2 nanoseconds, the time of a miss is 20 nanoseconds, and the miss penalty is 1 nanosecond. Okay. Perform cache mapping using fully associative with least recently used. Show all your work. Okay. Cache mapping's not too bad of a topic. It's just kind of depends on which type of mapping he's kind of using for this. So let's actually start with direct mapping first, because I think this one is a little bit, yeah, this one's actually a little bit easier to kind of wrap your head around. And then we'll go to fully associative LRU. Okay, so first things first, we're told we have a cache size of 4. So, right. And direct mapping uses the modulus function. So I take my memory address and I mod it by the size of the cache. So memory address mod 4. And I know that I could have a 0, a 1, a 2, or a 3. Right? You're just thinking of a remainder here. Okay. Now, each of these guys is going to be modded by 4 and placed in the proper box that it's supposed to go by. Now, if there's a collision, right, we simply will have to replace that, right? So with that being said, let's write that out. So we're going to be starting out with our 7. So 7 mod 4, right? That's going to be a remainder of 3. So our 7 is going to be going in this place. There's nothing in there right now, so no need to worry about having any problems with that, right? Now the next one, the 3 mod 4 is also going to be 3 now. Now we have ourselves a bit of an issue because we have a collision. This 7 is going to be now replaced by a 3. So with direct mapping, if you have a collision, you replace the value, whatever it is. It's directly going to where it needs to go. So I could end up having everything be in position 3 if my data was biased, and the rest of my cache is wasted. It's not even used, and I end up with a lot of collisions. So direct mapping is not always the best, but it does result in kind of a fair allocation in a sense, because it is like everyone gets a turn, first come, first serve, even if there is a collision involved. So even if they're all using the 3 spot, everyone's going to get a little taste of that 3 spot. So now
quick
we
question.
Yeah,
Before
what's up?
we go to the next number, do you recommend us crossing out 7 or not to do that?
I'm just doing it just so that I'm like, as I'm writing it out, that I don't miss any numbers.
No, I meant like in the mod 3, do you recommend crossing out 7 or not to?
As
Because
long as you can make it legible.
okay.
Yeah, I mean, this clearly shows us a change. The 7 has become a 3. So
Okay, yeah.
yeah, I'm just worried that like I'm gonna end up like doing like something really tiny and you can't really see it. So that's the only reason why I'm doing it that way. All right, moving on to 1, right? Now we change. 1 goes here in the 1 spot because 1 mod 4 is 1. So the 3 will also just remain there. All right, 2 is going to be the same thing. It goes in the 2 spot. The 1 and the 3 stay the same. 5 now, right? 5 mod 4. Okay, now we have the remainder of 1. The 1 gets replaced by a 5, and the 2 and the 3 stay the same. 4. Oh, finally, something goes in the 0 spot, right? 4 mod 4 is 0. So the 4, 5, 2, 3. Notice that up to this point, the cache was not full. Even though we had more than 4 entries, right? Because we had to do a lot of replacement. And that's okay. I mean, that kind of shows why direct mapping's not exactly the most efficient way of using your cache. But hey, for some applications, it works. Right? Continue onward. 5, right? 5. Oh, look at this. We have ourselves a hit, right? This is a cache hit. This guy is in my cache, right? So literally everything gets stayed the same. All of these before were misses. Misses because I actually had to write this into my cache, right? Each of these was not in my cache already. I had no repeated values. And because of that, right, every single time I had to erase a previous value and put in a new one. So when it comes to calculating later on the total time, we want to kind of keep track of the number of misses and hits. So with that being said, this is our first hit right over here when we get that 5. And for that matter, this 4 is also a hit as well, because look, the 4 is already here. I'm not changing my cache once again. 2. Wow, look at that, 3 in a row. That is another hit. Okay, now we don't get a hit, right? 6 is not in here. This is going to be 2, right? So that means 6 goes here. 5, 4, and 3 go here. This is once again going to be a miss, right? And I'm going to stop here because you kind of get the gist at this point, right? Direct mapping, you're essentially just, you're writing in where it goes based on your address, mod, the cache size. That's the most important thing to keep in mind. And you want to just kind of keep track of your hits and your misses, right? Because this comes into play when we find the total execution time, right? Total memory access time, right? We know that our TC is equal to 2 nanoseconds. Our time for a miss is equal to 20 nanoseconds. And our miss penalty is 1 nanosecond. Okay. And thankfully, the hardest part is honestly just putting this into the table. All right. Once you do that and identify what's a miss and what's a hit, it's literally a super simple formula, right? We know for this, the time of a cache is the time of a hit. And if you notice, it's so much less than the time of a miss because you don't have to actually go all the way into your memory. The whole point of a cache is that you don't go into your memory. You get to just use values that are hopefully commonly used that are in your CPU. All sorts of apps use caches. I mean, if you ever listen to music, they keep a cache of your most listened to tracks, and that way it loads really fast. That's the whole point of having a cache in the first place. In fact, I saw a funny meme that had saying, no, mom, the chair with all my clothes isn't just dirty laundry, it's an L1 cache so that I can access those clothes really fast. So that was kind of funny. But same premise, right? You do want to make sure that you could access values fast. And for the 3 hits that we had here, it worked. For the rest of them that were misses, not so much, but it's okay. So for this, right, we want to just kind of calculate the number of hits. We know that there were, I'm cutting it off here, right? Again, you have to do the rest of this on the exam and everything, but in just the interest of time, I want to try to make it through as many of these questions as possible. That way you get a gist of how it goes. So I'm going to stop at that point. So I know that I have 1, 2, 3 hits. 3 times 2 nanoseconds per hit, right? This is the time of a successful cache. I have retrieved it from my cache. Now for the misses, right? I have 1, 2, 3, 4, 5, 6, 7. 7 times 20 nanoseconds for a miss, plus an extra miss penalty, 21. Add them together. And again, do not actually do the calculation. Just write out how to do that. Okay. All right, is that clear? Before we move on to the next type of mapping. And by the way, if you have a second, please fill out the feedback form. We care a lot about your feedback and we hope that this was helpful. We're still going, don't worry, there's still time. But again, for future sessions, we want to make sure that this is helpful and if you have any feedback to give. So that's in the chat right now.
It is a little weird. I can't see this session in the form when I expanded. There's like nothing for October 10th.
Yeah, there's no
Give us one
CS343
moment,
in
we'll
the
update
form.
that for you. Thank you for letting us know.
Okay.
Okay, with that being said, let's move on to the next one. So I'm just going to clear this part out. That way we have a nice clean slate for the next one, right? Okay. So for the next one, we're going to do fully associative with LRU. So that just means least recently used. So this time we're not doing direct mapping based on the memory address mod 4. We still do have a cache size of 4. Yeah, because for the following string with cache size 4, yep. So with that being said, right, this time it's going to just be dealing with least recently used, right? Okay, 1 second. So we're able to use any of the free blocks, but for this matter, we could just kind of use like a first come, first serve. So using 0 first, then 1, then 2, then 3. So we know that the first 4 are going to definitely be misses, right? Because there's nothing in my cache right now. So 7, then a 3 is going to go in the next spot. Then a 1 is going to go in the next spot. Then a 2 is going to go in the next spot, right? So that part, we know we got miss, 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 miss. Now the cache is full. That's now when we need to use. So that's the fully associated part, right? It's literally a first come, first serve kind of deal. But now we need to care about our least recently used policy for who we kick from this cache. Before direct mapping, if you're in my spot, you get kicked out. Here with least recently used, it's the least recently used value. So this doesn't necessarily always mean the last one that was in. It just means the last one that was actually used. So this means that we're going to have to kind of go backwards a little bit to kind of see which one actually got used most recently. Or in this case, at least recently to get kicked out. So 5 is next, right? 5 is our next candidate. Okay, well, we know that the last one that was used was 7, right? 7 is the last one that was used. It's at the end of our line, you could say, right? So with that being said, actually, the way I'm going to do this, I'll still cross these guys out, but I'm going to put little dots here to show that these guys are still on the cache, right? You can think of them, they're still on the bus, or they're still on your carnival ride. You are on a carnival ride right now, and the person who was on the longest, right? They're going to get kicked off essentially in a sense, right? So if they were not used recently, they're going to get kicked off. So 7 is at the end here, right? So 7 is going to be the one to get kicked off. And 5 is going to go in its spot. Okay. Then, now, based on that, right? The next one here, actually, you know what I think I'm going to do instead of that? I'm going to just write, okay, 1, 2, 2. All right, now 1, 2, 3, 4, right? So this is now going to be based on the order, right? So 7 used to be 1, first one that was there. Now 5 is now the most recently used. 3 is now the least recently used, denoted by the lower number. So it's kind of like we're going up the block a bit. Okay, 4 is going to be next. Now 4 has to take on one of these positions. Which one is going to get it? Well, 3 is going to get kicked off because 3 has the lowest number, right? This was the least recently used. So I'm going to kick the 3 off, right? And that means that the 4 is going to go in the 3's spot. So the 3 was over here, 4 is going to go here, and these guys are going to be the same. Let me update the numbers now. 3 is gone. 2 now becomes a 1. This becomes a 2. This becomes a 3. 4 becomes the new 4, right? So now Let me write that out again. Actually, this is not really working. Maybe I'll just do it in a different color to try to clear that up then. Okay, 4 is the new 4, 5 is the new 3, 2 is the new 2, 1 is the new 1. Okay. Right. So with that being said, right, the 3 got kicked off. All right. Now we have ourselves a 5. So 5, on the other hand, now 5 is in the cache. So I don't need to worry about going over it. But now I need to update the 5 because now 5 is going to be the most recently used, right? Because 5 was used, now 5 becomes the highest value and the 4 goes down 1 pole. So it's as if they go back now to the front of the line, the 5. So 5 is not going to be kicked off now. Okay. And again, now we're on 4, right? 4 is going to be another cache hit, right? These guys were all misses. 4 is going to be another cache hit because, again, this guy is in here. So that's totally fine. I don't have to worry about doing a miss where I'm going to end up having to kick a value off. But now the 5 and the 4 switch places again because 4 was the most recently used. So 4 is going to take on the highest value now, and 5 is going to go one more step in line. So again, what is our line looking like? 1 and 2 are in the back, followed by a 5 and then a 4. So the next one that looks like it's going to get kicked off is going to be a 1, right? The one with the lowest value. Okay, 2 is going to be next, right? So in this case, 2 is actually in here. So this is great because now I don't have to worry about kicking off anything. This is going to be a 3rd hit. Okay, now I update it. So now 2 is going to take on the 4 value, right? Because it was most recently used. Oops. 2 is going to take on the 4 value. 4 is going to take on the 3 value. 5 is going to take on the 2 value. And 1 is still going to be here in the back with the 1 value. So the 2 went all the way back to the front of the line, basically. So this is why the numbers kind of come in handy a little bit, because it kind of tracks exactly who was most recently used. It's not just like, oh, who's just in, who was like last, who was in like, you know, first and first out, but it was who was actually used, which is kind of different than instead of frequent, right? Okay, so in this case, now we're going to have 6, right? So 6, this is indeed going to be a miss, right? This is not on here. Now, I know that because this is a miss, someone has to get kicked out. And who's going to get kicked out? The 1. So the 1 is getting kicked out, and the 6 is taking its place. Now, with that being said, right, I'm going to be having, just like move this over that, or okay, no, I have to still erase it. So the 6 now is going to be taking on the 4 value. This is 3, this is 2, and this is 1, right? So everything kind of gets shifted over 1, and the 1 was completely eliminated. Everything else stays the same. Maybe let's just do 2 more just to drive the point home. All right, 5 is the next one. 5 is still in my cache. So this is going to be a cache hit. So I'm doing good here. Now that the 5 is here, it was supposed to get kicked off on the last one. 5 is going back to the front of the line. So 5 is going to take on the 4 value. And the rest of these guys are going to go all down 1 value. 3, 2, 1. Okay. Now for the next value, 3, this is going to be a miss. It's not in my cache. Which value is going to get kicked off? The one with the lowest number, 4, right? 4 has the 1, 4 is the one that gets kicked off. So the 3 takes the 4 spot. The rest of these guys stays the same. And the new numbering is going to be 1, 2, 3, 4. Okay, and let's just do one more. We'll do the 2, right? So 2 is in my cache. So because of this, this is a hit. The 2 is here. So this is just going to stay the same. I just have to change my ranking now. The 2 is originally in the 4th position, goes to the front of the line. This becomes 1, 2, 3, 4. Right? And again, this continues on and on and on and on and on. So like here for the 7, which one gets kicked out? The 6, because it was least recently used, it has a value of 4, and continue on from there. So I'm going to just end it here for the time being, just so we could, in the interest of time, do one more like this. That way we could see kind of the difference with everything.
Just one quick question. What is your best advice to like just manage all these numbers? Because like just crossing them out and then figuring out the position, there is a lot. You get what I'm trying to say.
Yeah. You could honestly write it on the side, I would even say. Like I would literally right now be like having 1, 2, 3, 4, my positions here, right? 2 is in the 1 position, 3, 5, 6. Maybe crossing it out here might be a little better in a sense, right? Because the 6 would leave and then the 7 would come in. Something like that. Finding a way that kind of works for you in that regard is kind of the best way of doing it. The most important thing is if you don't have a way to keep track of the numbers, it's going to be very hard because otherwise you might think, oh, okay, well, I haven't dealt with the, let's say a 2 in a while, or 2 is all the way at the back of the line and you might have kicked the 2 off prematurely. So it's important to keep track of that. That's the whole reason why I put the numbers in there, because otherwise it would kind of be kind of hard to see like
Yeah. I was
why
like writing notes while you were doing this, and yeah, it just got really messy.
Yeah, again, this is recorded by the way, so please go back and like watch it. And also, like, if you need more help, I think you still have well over a week or so before your exam. So
He moved it. He moved
Oh.
it to 28.
Yeah, because we needed more time to finish the lecture.
And not only that, he also wanted to do a review session.
Yeah. I'm
Oh,
thinking I have to make my own individual one. Or like I have to make
Yes.
an amendment.
I think you can actually do another review session if you wanted to be honest.
Yeah.
yeah, actually, we could definitely do another review session. That could work totally. Yeah. Okay, wow. Okay, that changes things a lot. So you guys have a lot of time. So don't worry if this is confusing at first. You have plenty of time to practice.
It's not bad. It's just like just managing the numbers is just where the confusion happens.
Yeah.
If that makes sense. Because like what you're saying all makes sense. It's just managing the numbers. That's where it gets confusing.
What kind of helps me is honestly talking through it with myself on the exam. So like honestly saying in my brain, okay, I am kicking the 7 is my next term. The 6 is my least recently used, right? It has the 4. That's going to tell me, okay, I'm going to kick that off and put the 7 in its place and now change it. Kind of talking through it with yourself helps a little bit too. I mean, given the fact that we will probably have another review session for this, we can definitely go over more questions. And by the way, feel free, like we're also available at the Learning Commons for one-on-one appointments, or even if you want to do a group appointment, you can honestly go with a couple of your friends and like book an appointment with like a bunch of people. Like we don't mind, it's all the same for us. And like we can go one-on-one with these questions as well. So please do whatever you think will help you most. My best advice is just kind of keep practicing and know that you have time. Just keep reinforcing the material and you're going to be fine. His exams are very similar to these practice sets. I'm not saying, oh, it's identical, but if you understand why we're doing these steps and can do this on like another problem, which hint, AI can generate problems like this for you and check your work. So, life hack. If you can do that, then you're going to be totally fine on the exam. I promise you that. Yeah, I know it seems like a lot, but okay. Other questions? Also, the feedback form was updated with this course on it. So if you have a minute, please fill it out. And again, we can definitely do another review session as well. We have about 10 minutes left. So I'd be more than happy to answer any other questions you have, or whatever you want me to kind of go through.
Yeah, can you go over how to calculate the runtime again? Or the total time?
Absolutely, yes. Let's do it for this problem right here. So again, we only did up to this part over here where this red line is. So we'll just take into account over here, right? So I'm given the time of a cache, TC, time of a miss, and the miss penalty. So my formula for this is going to look like the time of a cache times the number of hits, oops, it's supposed to be an H, plus the time of a miss plus the miss penalty times the number of misses. Okay, so what this is referring to is I have my hits, which is the time that something is in the cache. And notice the time of a cache is much less than the time of a miss because you don't have to go into main memory. That's the main perk about this. So because of that, right, the time of my cache, which is going to be 2 nanoseconds, is going to be multiplied by the number of hits. I have 1, 2, 3, 4, 5 here. Okay. Plus the time of a miss plus the miss penalty. So that's 20 plus the 1 penalty, 21, times the number of misses. 1, 2, 3, 4, 5, 6, 7, 8. That's going to be your total memory access time. And again, you are going to do this for the entire problem. The only reason I didn't go the whole way is because I wanted to make sure we had enough time to go through these two and have questions and everything. But once you kind of get the gist of it, you can kind of keep going and going. And again, if you want to go over the question one-on-one in tutoring or in another review session, by all means, we are more than happy to help you with that. But as long as you kind of get the gist of that, right, you'd find the number of hits and misses continued, and that would obviously change the actual outcome of the formula, but you get the picture.
I'm not sure if you have time, but there's also another question asking for two-way set associative. If you can go over that.
Yeah, I think we should have enough time to do that one. Okay, so two-way set is associative with least recently used. So the difference here, right, is this time we have ourselves a two-way set. And we can think of it as this. We have a cache size of 4. And we know 4 divided by 2-way set is going to be 2. So that means I'm going to have 2 sets. So the way I'm going to do this is I'm going to break it down, break it up into half. So this is going to be set 1, and this is going to be set 2. Well, 0 and 1 if we're just talking about array notation, right? Now, when it comes to choosing which set it goes into, it's going to be based on our direct mapping, right? So if I end up going in this spot versus this spot, it's basically going to either be even or odd, right? So an odd number, like a 7, is going to go into 1. An even number, like a 2, is going to go into 0. Now, the if you notice, there's two spots inside of these guys, right? This part is going to be handling the least recently used part. So this is just going to say there's a least recently used set here, and there's a least recently used set here. So in the previous problem, we had only one least recently used stack, if you would say, right? It's kind of actually more like a queue in a way, because like the first one in usually is the first one out. Now we have two of these. So if I only have even numbers, I'm only using this part. If I only have odd numbers, I'm only using this part. And so because of that, right, we're kind of combining the two things that we learned about. This part involves direct mapping. These parts involve the least recently used. And now you can have as many sets as you want. Usually a problem will say 2, 3, or 4 sets. It's not going to be more than that. And you can also think about this, right? If I had 4-way set associative, that's literally just saying now I have 4 sets. That's just like 4 caches, which is literally what I'm used to. That's basically just direct mapping at that point. If I said that I had 1 big set, that's literally just LRU, exactly what we did before, right? 1 least recently used queue. Now with this, it's perfectly in half. So with that being said, we're going to be having exactly half on the top and half on the bottom. So let's do this for the problems here. And because there's going to be 2 queues, I'm going to just break it down based on these 2 parts. So I'm going to do it on both of these sides over here. Okay, so first things first, we have 7. Okay, so now 7 is going to be odd, right? So it's definitely going to be in this set over here. Now, of course, there's nothing here, so I could just put it in the first spot. No problem. We do know that is a miss though, because again, the queue is empty, the cache was empty. Okay. Next, we have a 3. 3 is also odd. Okay. 7, 3, miss. Okay. Now I know that I have a 1. 1 is also odd, so I know it's going in the second set. But now I need to say which one am I replacing. So it might be making a little bit more sense with the LRU as well when I have only these 2 that I have to worry about. So let's just kind of write it out like this. 1 and 2, right? So I know that I had 7 here first, but then once 3 came in the picture, it bumped the 7 down to the 2 spot. So that means when this 1 comes into play, the 1 is going to take the 7's position. So now the 1 goes in the first position and the 3 gets bumped down to the second position. So that's how we're keeping track of this, right? The one that was least recently used. Okay, so now 2 is my next one, right? Okay, even number, no problem. Fits right into my cache on the first one, right? Because 0, because it's an even number. So I'm using my other set. And no collisions there. But it is indeed a miss because it was not in there originally. All right, 5. Oh no, we got another odd number. My 2 is going to be the same, but now I have to decide which one am I kicking out. Well, it's going to be the 1 in the second place. So that's going to be the 3. So I have a 5 that takes the first spot. The 1 gets bumped down to the second. And I'm going to be having 1 and 5. So whatever is my least recently used is the one that gets bumped out. Okay. Next, I have 4, right? 4 is even. And there's still a spot in my even set that I can use. So this is no change to my, no collisions, right? It still is a miss, right? There wasn't a 4 there before, but now there is. So that gets taken out. Next, I have a 5. And for once, we finally have a hit. This is indeed in my cache. The key here, though, is now I need to keep in mind that the 5 was now more recently used, right? Which actually doesn't change anything because the 5 is still in the number 1 spot. But if it wasn't, it would have to get bumped up to the front of the line, essentially. Okay, we're done with 5. Now we're on to 4. Okay. While I'm at it, I probably should write out the same tier for the even side, right? 2 was the first one, but then the 4 bumped in and pushed the 2 to the bottom. So with that being said, right, we get 4 again. 4 is in here. So I know this is a hit and I'm not going to be changing anything at all. Also, 4 is already at the top, so it doesn't need to be bumped to the front of the line because it already is at the front of the line. 2 is my next one. Now 2 is in here already as well, so I'm going to have another hit. But I also have to do one more change. Now the 2 gets bumped to the front of the line because now it was most recently used. So the 2 goes before the 4 now. And now this is why when it comes to the next number 6, I'm going to have to, this is going to be a miss because it's not in my cache already. I'm going to have to kick something out. And know that for the last one, the 4 was kicked 1 tier down. Because of that, the 6 is going to be taking the 4 spot. Now, if I didn't have that least recently used policy, right? If I just had like a normal direct mapping or something, right? I might have actually written over that too. And because I have this least recently used policy, because the 2 had its redeeming shot, it was used most recently, that immediately makes it go up in a tier. So now the 6 comes into play though. So the 2 gets bumped down and the 6 now is in the number 1 spot. And my odd stays the same, of course. Okay, let's just do a couple more. 5 is my next one. 5 is in my odd cache right now. So because of that, that's just going to be a hit. 5 is also in my first spot of the line, so I don't need to worry about moving it either. All right, 3 is next. Okay, this is where we're going to be having a miss now. 3 is not in my cache. Which one do I kick off? Well, which one is in my bottom tier? The 1. So the 3 is going to be taking the 1 spot, and the 5 is staying the same. Everyone goes down a tier, so the 5 takes the 1 spot, the 3 takes the 5 spot. Okay, 2 is next. 2 is indeed in my cache. So this is a hit, but 2 is in the bottom spot. So this now goes to the front of the line. The 2 and the 6 now split. Okay, 7 is next. 7 is not in my cache. This is going to be a miss. Which one gets kicked off? The one in the lower position, the 5. The 3 stays the same. Okay, the 3 takes the 5 spot. The 7 takes the 3 spot. Okay, and let's just do one more, I guess. 2, right? We know this is going to be a hit because it's in my cache right now. And because this is already in the number 1 spot, no need to change it. Okay, so again, there's a couple more to go, but at this point you kind of get the picture. So with that being said, that's kind of what we're doing when we're doing two-way set associative mapping, right? We kind of combine the best of direct mapping with the best of least recently used. So notice that there was also less bookkeeping for me to keep. I didn't have to keep a queue of like 4 terms involved. It didn't get as messy. And I also knew exactly where things were meant to go. It's not like before where it's like, well, it could technically be in any position. Like it wasn't based on like the actual size, because we weren't really doing direct mapping in that case. It wasn't the address divided by the cache size. So this keeps things a little bit more organized without having to fully rely on either policy. And if you notice, we had quite a number of hits actually. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6, 7, 8, 9 misses. Okay, and if we were to do the total memory access time, notice they gave us different numbers. So let's take these guys into account. Total caches is going to be 3 nanoseconds. So that's going to be 6 hits times 3 nanoseconds plus 9 misses times the time of a miss is 20 and the miss penalty is 2. 20 plus 2, which is just 22. Okay, and then just multiple, like you could solve that, but again, you don't have to. This is totally fine to leave as your answer. Of course, doing this for the rest of this, but that's kind of how you do it. Also with the different numbers there. And yeah, any questions about that?
No, not really. To be honest, okay, so they're not bad, these types of questions. They're not bad. It's just tedious.
Yeah,
Right?
that's what I was gonna say.
Yeah, it definitely is.
If you were if on a Vivek test, which one do you recommend starting off with? Like, which one out of the 3 questions that we just did, like the 2 types of questions we did, which one is the most tedious, or the one on the exam right now?
Do yourself a
Do we
favor,
have-
do whatever is easiest for you. Don't like if the cache is easier for you, do it first. If what we did before here was easier for you, do that first. I'll be honest, I kind of feel like this is a little bit more intuitive because once you kind of get the rhythm of things, you can kind of just like write it out and just kind of like follow it like kind of like with the formula and everything. I think it's might be slightly quicker too because it's only like you're doing the cache mapping like just for this set of data. The other one, it's like we had to figure out, okay, this was looping 150 times. We had to go through each of these guys. I mean, in reality, I mean, of course, I took it much slower because, you know, we were going over it and everything. This is a review. In reality, it would be much quicker to solve, but it's still going to be tedious. All right. The only way you're going to get quicker at these things is by practice. The best way to study, which is the way I studied for it, is I literally would just do these problem sets over and over and over again until I no longer needed to like peek at the answer for like a hint or anything.
A
Like I'm gonna
follow-up question. For study sets, Vivek only released the exam only one example of the exam. Are the other exams available on Learning Commons?
I don't know if we have, okay, I know we do have more videos. I had tutored this class last semester as well.
Yeah, it would be nice to just have the blank copy so we can try them on our own before we watch the videos.
Right. Well, okay, I sent this one. Was this the one that you received?
Yes.
Okay. Right. I mean, I did send this in the chat as well, but I'll take a look at my video from last semester and I'll repost that in the Discord as well. And I'm not sure if this, I don't think these were the same problems because this part, like the offset definitely threw me off because I was not familiar with it. So I definitely think there was another previous exam or something from that. So I will send that in the Discord as well.
The blank copies?
Uh, if I have that, yes. If not, I know the
Okay.
video that I made would definitely have it as well, and you can maybe do the questions along with the video.
Okay.
Yeah. But yeah, the best thing to do, honestly, is just keep doing the problems over and over again. Like even over here, right? We have like another similar question, right? And a lot of these are going to require the same thing. Like this is actually a combination between the two, and we can honestly do that if we have another review session as well. This is involving the cache. It's one step further with a write miss policy. I'm not sure if you guys covered that yet. But again, like you're
not covered this at all.
Okay, that really explains a lot of why he postponed the exam then. Okay. Yeah, don't worry about this then. If you honestly want to do this problem, ignoring this part, you can. It's like some practice. Feel free to message me on Discord if you want me to check your work, by the way. Like I don't mind. But the best thing to do, honestly, is just keep practicing. And the practice problems he gives you, the practice problems are crucial. If you do those, it will definitely prepare you very well for the exam. But also remember, you have plenty of time and you can always just ask him questions. Like usually he'll always reserve like a few minutes in the beginning to answer any questions that students may have. So please definitely ask him questions, use your resources. Learning Commons is here to help you. We got a bunch of tutors that can tutor this class too. So you're not alone. And this will be up on the Learning Commons website too. So you can always rewatch this as well. Sorry if you hear a bird in the background. I think it decided it wanted to join the review session too. All right. Any other questions before we adjourn? And again, we can definitely have another review session if you guys want. But for now, just kind of take some time and just like take it in. It's a lot to do at first, but the more you practice, the better you get at it. And you can definitely do super well in the course. It's very, his exams are fair, honestly. Like I'm not going to say it's identical to this because it's not, but it's similar enough that if you truly understand these problems, you will do wonderful on the exams. Like he's not there to trick you. Maybe there will be a little trick somewhere in there, but it's not the entire exam, and you can do well just by knowing this material. So I promise you that. Any other questions before we end?
I had a question.
Yeah, go ahead.
So at the end of the execution, like, let's say the last line was like a 4,000. Like the PC is still updated to like 4004 if it was a 32-bit.
Yes, absolutely. So if this line over here, at the end, it would definitely be added 1 if it's 30. Sorry, it would be added 4 for the 32-bit system. So if it asked, for instance, what was the program counter for the end of the last instruction, you take that program counter and you add 4 one more time to it, because remember, it's going to the next instruction.
Yeah.
This one over here, which even though it's nothing, there still is an address for it.
All right. Thank you.
Another question?
Yes, I just want to know, for 343, what time do you learn are tutoring?
You can go on the Learning Commons website and book appointments with me. I have a variety of hours, some in the morning, some in the afternoon. So feel free to book that. I can give the link to that as well in the chat. So by all means, book an appointment with me, or some of our other tutors. I think quite a number of our tutors tutor for this class, so you should be fine. Yeah, have a great day, everyone, and don't forget.
Thank you so much for you. Have a great day.
Thank you.
Absolutely. Have a great day, everyone.